Today we're diving into section 12.4, focusing in on what is known as the law of sines. Now, when it comes to working with trigonometry, original trigonometry was built off of this idea of working with right triangles and trying to find missing sides and missing angles. But that's an awfully limited scope. So eventually, trig was adjusted to include how to work with other shapes or with triangles that are not right triangles. Now, the way that it was adjusted wasn't like they changed the trig. They just started to find patterns and ways that you could work with it in order to kind of move in the direction of doing trig with non-right triangles. Now, law of sines builds itself out of a basic formula. The formula for the area of a triangle. How do you find the area of a triangle? It's one we should know. Base times height divided by 2, or the more traditional formula is that the area is 1/2 base times height. But base times height divided by 2 works the same way. So, let's say I'm given a triangle. Looks like this. This is triangle ABC. Now, one of the things about triangles is if the vertices are A, B, and C, the side lengths are also shortened down to A, B, and C, but lowercase. Capital A is across from lowercase a, capital B is across from lowercase b, capital C is across from lowercase c. Now let's say that we know about this triangle, the length of A, the length of B, and the measure of angle C. Area of a triangle is 1/2 base times height. Do we have the information in A, B, and capital C to know the area of the triangle? Do we have the information necessary to calculate it? Do we have a base and a height, in other words? A base is the side of a triangle. The height is the distance across the triangle perpendicular to said base. Nah, we do not have a right angle in here, which means we do not have perpendicularity. If I am trying to find the area of this triangle, knowing these side lengths, let's just say I call this one the base just because it's easiest, it's on the bottom. I need the height to be right here. Now, even if I draw a triangle that looks differently from this, also call it ABC. I'm gonna have the same issue. In fact, the only way that I have both the base and the height of a triangle with knowing 2 side lengths of it is if it's a right triangle in the first place. But as I mentioned earlier, we're trying to move away from right triangles. Now in this triangle, if I count this as my base, the height is hanging out here. Do I have the information necessary to solve for the height? Keller's like, I don't see it, but I know the answer has to be yes. At least that's what it seems like you're trying to go for. Yes, we do. Because not only do we know two side lengths, we know an angle. And if you know side lengths and angles, you can solve for missing side lengths and angles using either Pythagorean theorem or trig. But so far we've learned Pythagorean theorem and trig using right triangles. Are there right triangles hidden in our pictures? Yes. Right here, for example, is a right triangle that I can work with, and I'm going to use that one instead of the one on the other side, because the one on the other side I know no information about. I don't know that length. I know what the full length would be, but I don't know this part, and I don't know that length, and I don't know an angle, so that's not helpful there. In this triangle, I can use right angle, I can use a right triangle, but I don't know anything about this right triangle, same issue, so I'm going to use the big right triangle that's technically in this picture. Now, if I look at those big right triangles, I don't know two side lengths of them. I only know one side length of them. What side length do I know? And it's the same one on each of them. What side length do I know in the right triangles if I know A, B, and capital C? The hypotenuse, and it happens to be A. And I also know angle C within them. So, that means this is my hypotenuse of my right triangle. I've got this angle, which means the height, which is the missing piece, is at the opposite, the adjacent, clearly not the hypotenuse. Is the height the opposite or the adjacent, given that I know angle C? Yep. It's the opposite. Therefore, I can say opposite and hypotenuse is which of our trig ratios? Sine. Or cosecant, but if we're trying to solve sine. So I know sine of angle C is equal to opposite over hypotenuse. And if I'm trying to solve for H, I multiply by A on both sides. A times sine of angle C is equal to H. And if that is H, then this formula for the area of a triangle can actually be rewritten. It can be rewritten in the situation where I know two side lengths and the angle between them. Area equals 1/2 base, which we called the base B. It's almost like I designed the triangle to keep that, times the height is A times sine of angle C. This is what is known as the side angle side area formula. Traditionally, it's written like this. Now, this is not law of sines. We're not to law of sines yet. This brings us eventually to law of sines. But this formula works great for solving for the area of a triangle if you know two sides and the angle between them. That's why it is called side angle side. Two sides, angle between. So, before we get to the true law of sines, one of the things you're going to be asked to do today is to find the area of a triangle. We're going to round our answer to the nearest hundredth. Sometimes when they give you this question, they're going to give you a picture of a triangle. Now, key thing to use this formula, it needs to have two sides and the angle between. If you do not know two sides and the angle between them, you can't use it. Do we know two sides and the angle between? Yeah. Now, the formula works with A, B, and C, just to reference back to triangle ABC. The key thing you need to know is lowercase letters are side lengths, angles are capital letters, and the fact that all three of them are different letters is what tells us that it's two sides and the angle between. Because if this is triangle D, E, and F, side D would be over here, side E would be this one, side F would be this one. Essentially, when you have those side lengths, the angle between them is going to have a different letter when you name a triangle properly. Okay, so I do have two sides and the angle between, so I can plug in. Does order matter in multiplication? No, so it doesn't matter which side you put in first. So, we plug what we know into the formula and we grab a calculator and we start typing things in. Rounding to the nearest hundredth is how many decimal places? 2. What do you get? 101.98. It's an area. 101.98 what?
Squared.
What squared?
Units.
If you don't know what they are, you write units. If you knew it was feet, centimeters, meters, whatever it might be, then it's that squared. But it is area, so it's units squared. Sometimes, when they give you these problems, they will not give you a picture. They'll give you a description of a triangle. They'll tell you something like it's triangle XYZ with X equal to 8, Y equal to 9, big X equal to 37 degrees, and big Y equal to 39 degrees. Now, if you wish, you can draw yourself a triangle. If you don't wish to do so, you don't have to. But you do need to know if you have two sides and the angle between to use this formula. Do you notice you know side x and side y and angle x and angle y? Do we have two sides and the angle between them?
Yes.
Really?
No.
We don't. We do not have two sides and the angle between. Because two sides and the angle between are going to have three different letters. I only have x's and y's. Yeah, there's capitals and lower cases. That's the difference between sides and angles. Does that mean we can't solve it? No, it doesn't mean we can't solve it. Because if you know two angles in a triangle, no. Pythagorean theorem, first off, only works on right triangles. Do you have anything indicating it's a right triangle? No. Second, there's a different direction we're going to go, and I mentioned angles. If you know two angles in a triangle, how do you find the third? Angles add up to 180 on a triangle. So, what's the missing angle's name, by the way?
Z.
Capital Z specifically. Z is 180 minus the two angles I know. By the way, how do I know that it's the 37 and the 39 that are the angles? Capital letters, and they have the degree symbol. Both of those things. Okay, so angle Z is 104 degrees. Definitely not a right triangle. It's an obtuse triangle because it's got an obtuse angle in it. Now do I have two sides and the angle between? Yeah. Area equals 1/2 times side length times sine of angle between. What do you get? Anyone? 34.93 units squared. Okay. So, that's one thing you're going to see today. But, is that our end goal? No. What's the name of the section? Law of sines. Our goal is to get to the law of sines. So, law of sines, as I mentioned earlier, builds its way off of this formula. And as I mentioned, that formula is coming out of working with triangle ABC. That formula assumes that the side lengths that I know and the angle I know on triangle ABC is this side, and that angle. When you're given a triangle, does it matter which two sides and which angle you know to find the area? As long as the angle's between them? So, this is one version of the equation of law of sines for this triangle, but it's not the only one. I could have had this side, and that angle, in which my formula would have said area is equal to, can we stop with side conversations, please? Area is equal to 1/2. Now my side lengths are B and C, and the angle between them is angle A. Or I could have had these two sides in the angle between, to where the area would have been 1/2 AC sine of B. Would you agree that if it is the same triangle, that all three of those should get you the same result? Therefore, I missed something. Let's try that again. Therefore, I can say this is equal to this, which is also equal to this, but I need to make it a little smaller to get it to fit on screen. All of those are equal. That looks like a big, ugly, long equation, right?
Yeah.
Okay, let's make it easier to work with. Do you notice that every single, and yes, I'm going to work with 3 different sides of an equation. Do you typically work with that? No, I don't care. Do you notice that all 3 of them have the 1/2 on it? If you multiply all 3 by 1/2, is it really doing anything? No. So, I can essentially divide by 1/2 across, and that'll disappear, that'll disappear, and that'll disappear. Beautiful. Looks a little bit better. Not much, but a little bit. Do you notice that all 3 have an A, B, and a C in them? It'd be really nice if we could simplify it down to where there's fewer things on each equation, fewer letters. So I want to get rid of these things in front. They're being multiplied, right? How do you undo multiply? Divide. I'm going to divide all of them by A. Okay, as I divide by A, these A's are going to cancel. Nothing's canceling here. These A's are canceled. Can I do the same thing with B's and C's? B cancels. B and C both cancel. C cancels. Looking a little bit nicer. How many sides of an equation do I actually need, though? Do I really need 3 parts? No, I only need 2. That is the law of sines. Law of sines says sine of capital A over A equals sine of capital B over B. Law of sines is used to solve for missing angles or sides. In non-right triangles. Don't get me wrong. You can use law of sines for right triangles. You really can. You just don't need to. SOHCAHTOA tends to be faster and easier. Now, to use law of sines, there are 4 unknowns that go in. 2 angles, 2 sides. If you are trying to solve and you have a single equation, how many things can be unknown? How many variables can you actually solve for if you only have 1 equation? 1. That's something you would have talked about when you did system of equations. If you want to solve for 2 variables, you need 2 equations. You want to solve for 3 variables, you need 3 equations. So, in order to do law of sines, I need to know at least either one angle and 2 sides, or one side and 2 angles. Now here's a weird thing about law of sines. It is possible to have multiple solutions. In certain cases. If you go into this and you know 2 angles from the very beginning, there will only ever be one triangle possible. But if you go into this where you know 2 of the sides, it's possible to have 0, 1, or 2 triangles that work. This comes out of the fact that when you were doing just straight up right triangle trigonometry, you were always going to work with angles between 0 and 90 degrees, because to do trigonometry in a right triangle, you have to look at one of the acute angles in the right triangle. And so what ended up happening, if I pull out my unit circle just to show you, you don't really need your unit circle today. If you were only working with angles between 0 and 90 and you were doing sine, you were always going to end up with situations where the answers were unique solutions. On the alternative, though, when now you're working with non-right triangles where angles can measure anywhere between just over 0 and just under 180 degrees, do you notice sine is what part of the unit circle? The y values. Do you notice that there are places where y values match?
Yes.
Which means if I'm trying to solve for missing angles, inverse trigonometry, the calculator itself will only give me angles between 0 and 90 degrees, but angles between 90 and 180 will also work when solving for angles and triangles. And so we have to address that if it comes up. That's why multiple triangles can be possible in situations where you only know 2 sides and your first thing you're going to be doing is trying to find angles. So, today, the examples are going to ask you to solve the triangle. Note it didn't say solve for a missing piece of the triangle. It said solve the triangle, which means find all missing pieces. All missing sides, all missing angles. We will round for notes, sides, when we get back.
Where's the worksheet?
Okay, we're going to round sides to the nearest hundredth. And angles to the nearest degree. Now, I mentioned this before lunch. When it says solve a triangle, what are you actually solving for? All of the missing sides, all of the missing angles. Now, today we're just going to be focusing on the law of sines version where I'm starting off giving you 2 angles. So we're just going to deal with the version of the law of sines that one triangle is possible. On Monday, we will get into the knowing two sides and having multiple triangles possible and how to address that. So today we're just trying to get our feet wet with law of sines. So some of the times you're going to be given a picture. I'm going to start out with triangle Q and P. Angle Q is a 65-degree angle, angle P is 42 degrees, and side QP is 5. Now, I called that side QP because in geometry, that's what you would have called it. What side is it when we're working with trig, though? It's lowercase a. What's that one? Lowercase p. This one? Q. Goes with across. Q, Q, P, P, N, N. They're across from one another. My goodness. Okay, now, if this was a right triangle, I'd be looking at doing some trigonometry like SOHCAHTOA trig. Is it a right triangle? No. So I can't do SOHCAHTOA trig. So that's where law of sines comes into play. To do law of sines, though, because of its setup, sine of A over A equals sine of B over B, I have to know 3 of these things, which means I have to know an angle and a side across from one another. Do I have that? Not currently. Can I find that? Yes, because angles of a triangle add up to 180. So I can find angle N. 180 minus the 2 I know. In general, when doing law of sines, you're always really kind of going to find a third item that you already know 2 of. Okay, 180 minus 65 minus 42. N is 73 degrees. Now, again, with degrees, do not forget the degree symbol. And also, you have to pay attention to your capital and lowercase letters. Some of y'all use them interchangeably. Nope. Capital letters are angles, lowercase letters are sides. Okay. Now, to use law of sines, as I already mentioned, you need to know an angle and a side across from it because of the fact that it's set up sine of A over A, sine of B over B. The way that the actual formula works is that those are across from one another, those are across from one another. So I always just kind of start off with doing sine of the angle I know that I also know the side across from it. I know that I have a 73-degree angle over the side across from it is 5. Equal to sine of an angle over the side across from it. Now, generally speaking, and this is going to become more important as we keep going through chapter 12, so I just kind of start you off in doing this from the beginning. It's not technically a requirement with law of sines. Your best bet is to solve for the biggest item that's missing. It's going to actually end up saving you situations in the future when it comes to when we get into law of cosines specifically. How do you know if if P or Q is bigger? Side P or side Q? I have no Goku, what you said. Has to do with the angles. Think about a triangle. The wider that an angle is, the larger the side across from it has to be. Because as an angle opens wider, the side to connect has to be longer. It's really just kind of how it works. So, between angle Q and angle P, which one's bigger? Q, it's 65, which means side Q is going to be bigger than side P. So I'm going to solve for side Q. I'm going to put angle Q in, and then Q goes there. How do I solve equations that look like fractions equal to fractions? Cross multiply. This is called a proportion. Fraction equal to a fraction. You can cross multiply to solve. So, Q gets multiplied by sine of 73, which is Q times sine of 73. Equal to 5 gets multiplied by sine of 65, which is 5 times sine of 65. Now, just a quick reminder to selves. Can I multiply the 5 and the 65? No. How do I get Q alone? Divide by sine of 73. It's not pretty, but that is a really calculator-friendly equation. 5 sine of 65 getting divided by sine of 73. Make sure you are closing your parentheses on your TIs. Rounded to the nearest hundredth. 4.74. Okay? I found one missing angle. I found one missing side. I still have one missing side. I still need to find side P. If I know two sides of a triangle, can I use Pythagorean theorem to find the third?
No.
Only if it's a right triangle. Don't do it. Every single year, people do law of sines to find the first side, and then they try to do Pythagorean theorem. Pythagorean theorem and SOHCAHTOA trig are right triangle uses only. How can I find the last side? Don't overthink it. We have a formula that connects sides and angles of non-right triangles. It's called the law of sines. You just do it again. Sine of 73 over 5 equals sine of 42 over P. You start with sine of an angle you know over a side across from it you know equal to sine of an angle you know over the side that's missing. And you cross multiply to solve. P sine of 73 equals 5 times sine of 42. To get P alone, we divide by sine of 73. Rounded to the nearest hundredth, what do you get? .50. Now, one of the things that you're going to want to do when you finish working with law of sines and law of cosines for that matter. Now, it shouldn't become a problem on today's stuff, but it can become a problem, is in all actuality, you should check that the triangle makes sense. What do I mean by that? The biggest angle should be across from the biggest side. Same with smallest. Every once in a while, when we are working with law of sines and law of cosines, those situations where there's multiple triangles possible is especially when this can come up, but it's not the only time. In all technicality, when we do get to the part that works with multiple triangles possible, they give us a setup and a formula and things to check to see if the triangle's possible. In my experience, it's the hardest way to do it. So I teach you an easier way, but every once in a while, there's the occasional triangle that slips past the easier way. To kind of shore that up, if you check the triangle makes sense, it will take care of that problem. Okay, these two and this side are my three sides. Biggest one's 5. It's side N, so angle N better be the biggest. Is that the biggest angle?
Yes, it is.
Smallest side's 3.5. Smallest angle's 42. Are those across from one another? Sweet, we're good. 95% of the time, it's going to work out beautifully. Haven't you figured out by now that I always try to like give you prove it?
33 more.
Okay.
Prove it on the on with enough to prove it.
Hey, no, hey, we're doing this.
On a room.
Rude.
It's fine. He doesn't. He's not. She's gonna pull it.
Okay. You supposedly know it. I'm going to make you prove it. I'm grabbing a problem directly off the homework.
Yeah, wait, which
If
number?
you solve it correctly, I'll tell you which number. In the meantime, I'm going to do the problem too. That way it's on the video correctly.
How do you know we're not gonna do it correctly?
The one thing that I did not mention that I do recommend with these problems, in the situations where you're not given a picture, I recommend you do draw a generic picture just that gives you the idea of where things are located on the triangle. You don't have to measure out the angles to where they make sense. Clearly, that is not a 20-degree angle. But just drawing it out, labeling the corners so that you can label the sides does tend to help a lot of people from making mistakes.
You messed up. Yeah, you already messed up. It's 31, not 13.
I'll fix it. You right.
Yeah.
works better.